Tonight, we begin with something that sounds impossible, yet exists everywhere around us. Time itself bending, stretching, flowing at different speeds depending on where you are in the universe. And nowhere is this more profound than near the most mysterious objects we know, black holes. These cosmic giants don't just swallow light and matter, they bend the very fabric of time itself. So settle in, maybe dim the lights, and let your mind drift as we explore one of the most beautiful and mind-bending phenomena in all of physics. How gravity itself can slow the passage of time, how a clock near a black hole ticks differently than one on Earth, and why understanding this changes everything we think we know about the nature of reality. In a moment, we'll journey to the edge of space-time itself. But first, let me paint you a picture that will help everything else make sense. Imagine you're floating peacefully in space, watching two identical clocks. One drifts near you in the gentle emptiness between stars. The other falls slowly toward a massive black hole in the distance. As you watch, something extraordinary happens. The clock near the black hole begins to tick more slowly. Not because it's broken, not because of some mechanical failure, but because time itself is flowing differently there. This isn't science fiction. This is the universe we actually live in. A place where time is not the steady, unchanging river we experience in our daily lives, but something far more fluid and mysterious. Einstein showed us this more than a century ago, and every experiment since has confirmed what seems impossible. Gravity doesn't just pull objects through space, it pulls on time itself. The story begins in 1915, when Albert Einstein published his theory of general relativity. It was a radical departure from everything humans had believed about the cosmos. Newton had given us a universe where space and time were separate, absolute, unchanging stages upon which the drama of physics played out. Einstein revealed something far stranger and more beautiful. Space and time are woven together into a single fabric called space-time. And this fabric can be bent, stretched, and curved by the presence of matter and energy. Picture space-time as a vast, invisible trampoline stretching infinitely in all directions. When you place a bowling ball in the center, the surface curves and dips around it. Now roll a marble across this curved surface. It doesn't travel in a straight line anymore. It follows the curves created by the bowling ball, spiraling inward in what we call an orbit. This is gravity, not a force pulling objects together, but the natural motion of things following the curved paths through space-time. But here's where it becomes truly extraordinary. Time is part of this fabric too. When space-time curves around a massive object, it doesn't just bend the paths that objects take through space, it bends the flow of time itself. The stronger the gravitational field, the more dramatically time is affected. Near a black hole, where gravity reaches its most extreme, this effect becomes profound beyond imagination. To understand why this happens, we need to think about what time actually is. Time isn't some external clock ticking away in the background of the universe. Time is deeply connected to the speed of light and the structure of space-time itself. When space-time curves, it changes the very geometry through which light travels. And since time is fundamentally linked to how light moves through space, time itself changes. Near a black hole, space-time is curved so severely that something remarkable occurs. The dimension of time itself gets compressed, squeezed by the immense gravitational field. It's as if the universe is gently pressing down on the flow of time, causing it to move more slowly relative to regions where space-time is flatter and gravity is weaker. Now, here's something crucial to understand, and it might seem contradictory at first. If you were near that black hole, you wouldn't feel time moving any differently. Your watch would tick at exactly the same rate it always has. Your heartbeat would be steady and normal. Your thoughts would flow at their usual pace. To you, time would feel completely ordinary. This is one of the most beautiful aspects of relativity. Each observer experiences their own time as normal, flowing at its natural rate. The magic happens when we compare different observers in different gravitational environments. Imagine you have a twin who stays safely on Earth while you journey to orbit a black hole. From your perspective near the black hole, everything seems normal. But if you could somehow watch your twin on Earth, you would see their clock ticking faster than yours. Their day would pass more quickly. Their seasons would change more rapidly. Years would flow by on Earth, while you experience only hours or days. Meanwhile, your twin on Earth would see something equally remarkable but opposite. Watching you near the black hole, they would see your clock ticking more slowly. Your movements would appear sluggish. Your day would stretch out far longer than theirs. To them, you would seem to be moving through time in slow motion. Both perspectives are equally valid. Both are true. This is the profound insight of relativity. There is no universal, absolute time ticking away the same for everyone everywhere. Time is relative, flowing differently for observers in different gravitational environments. It's a concept that challenges our everyday intuition, but reveals a universe far more elegant and interconnected than we ever imagined. The mathematical description of this phenomenon comes from what we call the Schwarzschild metric, named after Carl Schwarzschild, who found the solution just months after Einstein published his field equations. Tragically, Schwarzschild died shortly after his discovery while serving on the Russian front during World War I. But his work gave us the first complete picture of how space-time behaves around a spherically symmetric massive object like a black hole. The Schwarzschild metric tells us exactly how time dilation changes as you move closer to a black hole. At large distances, the effect is barely noticeable, but as you approach the black hole, time dilation becomes more and more pronounced. At 3 times the Schwarzschild radius, the point that defines the black hole's event horizon, time flows at about 81% the rate of a distant observer. This means that if an hour passes for someone far from the black hole, only about 48 minutes pass for someone at this orbital distance. Move closer, and the effect becomes even more dramatic. The mathematics shows us that as you approach the event horizon itself, time dilation approaches infinity from the perspective of a distant observer. This creates one of the most haunting and beautiful predictions of general relativity. To someone watching from far away, an object falling into a black hole would appear to slow down more and more as it approached the event horizon, seeming to freeze at the boundary, never quite crossing over. But this is only from the external observer's perspective. For the falling object itself, time continues to flow normally. They would cross the event horizon in a finite amount of their own time, experiencing nothing unusual about the passage of time itself. It's a perfect illustration of how perspective shapes reality in Einstein's universe. The event horizon represents a boundary unlike anything else in physics. It's the point of no return around a black hole, where the escape velocity equals the speed of light. Beyond this boundary, not even light can escape the black hole's gravitational pull. The size of this boundary depends entirely on the mass of the black hole. For a black hole with the mass of our Sun, the event horizon would have a radius of about 3 kilometers. For the supermassive black hole at the center of our galaxy, with a mass of 4 million suns, the event horizon stretches to about 12 million kilometers. These supermassive black holes create fascinating scenarios for time dilation. Because their event horizons are so large, the tidal forces, the stretching effects of gravity, are much gentler than around smaller black holes. This means you could actually cross the event horizon of a supermassive black hole without immediately being torn apart. You might survive long enough to experience the profound time dilation effects firsthand. Near such a black hole, the time dilation effects could be so extreme that a brief visit might last years or decades from the perspective of the outside universe. This isn't just theoretical speculation. It's a direct consequence of the mathematics of general relativity, equations that have been tested and confirmed in countless experiments and observations. We see evidence of gravitational time dilation all around us, even here on Earth. The Global Positioning System, GPS, provides a perfect real-world example of these effects in action. GPS satellites orbit about 20,000 kilometers above Earth's surface, where gravity is slightly weaker than at ground level. This means time flows slightly faster for the satellites than it does for us on the surface. The effect is tiny, only about 38 microseconds per day, but it's measurable and significant. If this time dilation weren't accounted for, GPS would become completely useless within hours. Your navigation system would accumulate errors of several kilometers per day. The entire system depends on precisely synchronized clocks, and even this tiny difference in the flow of time would destroy that synchronization. Engineers have to program the satellite clocks to run slightly slower before launch, compensating for the gravitational time dilation they'll experience in orbit. This everyday technology proves that time dilation isn't just an exotic effect relevant only to extreme environments like black holes. It's a fundamental feature of our universe, operating at all scales, in all gravitational fields. Even the modest gravitational field of Earth is enough to measurably affect the passage of time. The effects become much more dramatic around more massive objects. Astronomers have observed stars orbiting close to the supermassive black hole at the center of our galaxy. In 2018, a star designated S2 made its closest approach to this black hole, traveling at about 2,500 kilometers per second, roughly 2.5% the speed of light. At this closest approach, the star experienced significant gravitational time dilation and redshift, effects that were precisely measured and found to match Einstein's predictions perfectly. This observation represents one of the most direct confirmations of general relativity in the strong field regime, where gravitational effects are most pronounced. The star's light was stretched to longer, redder wavelengths as it climbed out of the black hole's gravitational well, a phenomenon called gravitational redshift that's intimately connected to time dilation. As we continue our gentle journey into the heart of this mystery, we'll explore what it would actually feel like to experience extreme time dilation firsthand. We'll visit different types of black holes and discover how their size affects the time dilation they create. And we'll uncover how these seemingly abstract concepts reveal profound truths about the nature of time, space, and our place in the cosmic order. Order, the beauty of gravitational redshift, reveals itself in the most elegant way when we observe light escaping from these deep gravitational wells. As photons climb out of the curved spacetime around a black hole, they lose energy, stretching to longer wavelengths, shifting toward the red end of the spectrum. This isn't just a theoretical prediction. It's something we can measure with our most sensitive instruments, a visible manifestation of how gravity affects not just matter, but the very essence of light and time itself. White dwarf stars, those dense remnants of sun-like stars, provide us with beautiful examples of this phenomenon. The surface gravity of a white dwarf is so intense that light escaping from its surface is redshifted by about 50 kilometers per second relative to the speed of light. That translates to roughly 170 parts per million, a tiny but measurable shift that our telescopes can detect with remarkable precision. When astronomers first observed this redshift in white dwarf starlight, they were witnessing direct evidence of space-time curvature. Each photon of light carries with it the signature of its journey through curved space-time, a cosmic fingerprint that tells us about the gravitational environment from which it escaped. It's as if the universe is constantly sending us messages written in the language of light and time. Near black holes, these effects become far more pronounced. The gravitational redshift becomes so extreme that light from objects near the event horizon is stretched to radio wavelengths by the time it reaches distant observers. This creates a natural fade-out effect, where objects falling toward a black hole gradually disappear from view, not because they've been destroyed, but because their light has been redshifted beyond our ability to detect it. This brings us to one of the most profound aspects of black hole physics, The event horizon itself represents a boundary in space-time where our ability to observe events comes to an end. From the perspective of an outside observer, time dilation becomes so extreme at the event horizon that clocks there would appear to stop entirely. But this is purely an observational effect, a consequence of how light travels through the severely curved spacetime near the black hole. For someone actually crossing the event horizon, time continues to flow normally. They would experience no sudden change, no dramatic slowing of their personal clock. Their heartbeat would continue at its natural rhythm. Their thoughts would flow at their usual pace. The event horizon, from their perspective, would be crossed in a finite amount of time, perhaps just a few seconds or minutes, depending on the mass of the black hole. This creates a fascinating paradox that has puzzled physicists for decades. How can an event both happen and not happen, depending on who's watching? The resolution lies in understanding that there is no single universal perspective on time. Reality itself depends on your reference frame, on where you are and how you're moving through space-time. The size and type of black hole makes an enormous difference in these time dilation effects. Stellar black holes, formed from the collapse of massive stars, are relatively small and dense. A typical stellar black hole might have a mass 10 times that of our Sun, compressed into a sphere just 60 kilometers across. Near such an object, the curvature of space-time is extremely sharp, creating intense tidal forces that would stretch and compress anything approaching the event horizon. But supermassive black holes, the giants that lurk at the centers of galaxies, create entirely different environments. The supermassive black hole at the center of our own Milky Way galaxy, known as Sagittarius A star, contains the mass of over 4 million suns. Yet its event horizon stretches across 24 million kilometers, roughly the distance from Earth to Venus. The curvature of space-time around such massive objects is much gentler, spread out over vast distances. This has profound implications for time dilation. Near a supermassive black hole, you could potentially orbit very close to the event horizon and experience dramatic time dilation effects without being immediately torn apart by tidal forces. You might spend what feels like hours or days in orbit, only to discover that years or decades have passed in the outside universe. The mathematics of this effect are both beautiful and precise. Einstein's field equations tell us exactly how time flows at any distance from a black hole. At twice the Schwarzschild radius, time flows at about 70% the rate of a distant observer. At 1.5 times the radius, it's about 58%. As you approach the event horizon itself, the time dilation factor approaches infinity, creating that strange frozen moment from the external perspective. But here's something remarkable to consider. The observer falling into the black hole would see the outside universe speeding up. As they fall deeper into the gravitational well, they would watch the stars wheel overhead at an accelerated pace. They might witness the birth and death of stars, the slow dance of galaxies, the eventual evolution of the cosmos itself, all compressed into their final moments before crossing the event horizon. This reveals something profound about the nature of perspective in our universe. There is no privileged viewpoint, no universal clock keeping time for everyone. Each observer carries their own piece of time with them, experiencing their own flow of moments, their own sequence of cause and effect. Time is not a river flowing uniformly towards some distant ocean. It's more like a vast landscape with valleys and hills, where the pace of flow depends entirely on where you happen to be standing. The concept of frame dragging adds another layer of complexity to time dilation around rotating black holes. When a massive object spins, it literally drags the space-time around it into rotation, like honey being stirred with a spoon. This effect, predicted by Einstein but only recently confirmed through precise observations, means that space-time itself has a kind of viscosity, a resistance to changes in rotational motion. Around a rotating black hole, described by the more complex Kerr metric, time dilation becomes dependent not just on distance, but on direction. An observer orbiting in the same direction as the black hole's rotation would experience different time dilation than one orbiting in the opposite direction. The rotating black hole creates a kind of whirlpool in space-time, carrying everything nearby along with its motion. This frame-dragging effect has been measured around Earth itself, though the effect is incredibly tiny. Our planet's rotation drags space-time around it by just a few millimeters, but sensitive satellites have detected this effect, confirming yet another prediction of Einstein's theory. Around a rapidly spinning black hole, the effect becomes much more dramatic, creating regions where it becomes impossible to remain stationary relative to distant stars. These insights have led physicists to some remarkable realizations about the nature of time itself. Time is not separate from space. It's not independent of matter and energy. Time is woven into the very fabric of reality, shaped by mass and motion, curved by gravity, flowing at different rates depending on where you are in the cosmic landscape. This understanding has practical consequences that extend far beyond academic physics. Every GPS satellite in orbit experiences time dilation due to both its motion and the reduced gravitational field at its altitude. The combination of these effects causes satellite clocks to gain about 38 microseconds per day relative to clocks on Earth's surface. This might seem insignificant, but without correcting for this time dilation, GPS would accumulate position errors of several kilometers per day. Engineers compensate for this by programming the satellite clocks to run at a slightly different rate before launch. They set the clocks to tick at 10.229999543 MHz instead of exactly 10.23 MHz, accounting for the time dilation the satellites will experience once in orbit. This remarkable precision demonstrates how deeply Einstein's insights have penetrated into our everyday technology. And the philosophical implications of time dilation extend far beyond physics. If time itself is malleable, shaped by gravity and motion, what does this tell us about the nature of existence? Are our human experiences of past, present and future merely local phenomena, relevant only to our particular corner of space-time? In regions of intense gravity, the very concepts of before and after become ambiguous, dependent entirely on the observer's reference frame. Consider the profound loneliness that time dilation might create. An astronaut spending time near a black hole would return to find that everyone they knew had aged far more than they had. Friends and family would have lived entire lifetimes, while the astronaut experienced perhaps months or years. The universe itself would have evolved. Stars would have been born and died. Civilizations might have risen and fallen, all while the astronaut experienced a relatively brief journey through curved space-time. Yet this same effect offers a kind of immortality, a way to journey far into the future of the universe. By spending time in regions of intense gravity, one could witness the long-term evolution of the cosmos. You could watch galaxies merge, see how the universe changes over millions or billions of years, all while aging only slightly yourself. Time dilation provides a natural time machine, though one that travels only in one direction, toward an unknowable future. The study of time dilation near black holes has also revealed deep connections between gravity, thermodynamics, and information theory. Black holes appear to have temperatures and entropies, as if they were thermodynamic objects rather than merely gravitational ones. The event horizon area is related to the black hole's entropy, suggesting that information might be encoded on the boundary of space-time itself. These insights have led to revolutionary ideas about the nature of reality. Some physicists now suspect that what we perceive as three-dimensional space might actually be encoded on two-dimensional surfaces, like shadows cast by higher-dimensional objects. The holographic principle, inspired by black hole thermodynamics, suggests that reality itself might be fundamentally different from our everyday experience. As we drift deeper into this meditation on time and space, we begin to see how the universe reveals its secrets through the gentle warping of space-time around massive objects. Every black hole becomes a natural laboratory for studying the most extreme physics, places where the familiar laws of everyday experience give way to something far stranger and more beautiful. The detection of gravitational waves has opened yet another window into these extreme environments. When two black holes spiral together and merge, they create ripples in space-time itself, waves that travel outward at the speed of light, carrying information about the collision across the cosmos. These waves, predicted by Einstein but only recently detected, provide us with a new way to study black holes and the time dilation effects in their vicinity. During the final moments before two black holes merge, the space-time around them becomes incredibly dynamic. Time dilation effects fluctuate rapidly as the gravitational fields change and interact. The merger itself happens in a burst of gravitational radiation that lasts only seconds, but contains more energy than all the stars in the observable universe combined. In those final moments, the very fabric of space-time rings like a bell, creating patterns of time dilation that ripple outward across the galaxy. These observations have confirmed Einstein's predictions with extraordinary precision. The gravitational waves detected by our instruments match the theoretical predictions to within a fraction of a percent, providing compelling evidence that our understanding of spacetime and time dilation is fundamentally correct. The universe really does behave according to the elegant mathematics of general relativity. As we contemplate these cosmic scales and the malleable nature of time, we begin to appreciate how small and brief our human experience really is. The time dilation effects that seem so dramatic to us are tiny perturbations in the vast symphony of space-time. A lifetime spent near a black hole might slow time by factors of hundreds or thousands, but the universe itself has been evolving for nearly 14 billion years. Even the most extreme time dilation effects are mere moments in the cosmic story. Yet there's something deeply moving about our ability to understand these phenomena. Here we are, brief arrangements of matter and energy, contemplating the nature of time itself. Through careful observation and elegant mathematics, we've learned to peer into the hearts of black holes, to understand how gravity shapes the flow of time, to glimpse the fundamental structure of reality. In the gentle darkness of space, where stars shine like distant lighthouses across vast oceans of time, black holes continue their ancient dance, warping space-time, slowing time, creating pockets where the universe experiences itself at different rates. And somewhere in this cosmic landscape, on a small planet orbiting an ordinary star, conscious beings pause to wonder at the mystery of time itself, finding in that wonder a kind of peace, a sense of connection to something vast and beautiful and eternal. A sense of connection to something vast and beautiful and eternal. This brings us to a question that has puzzled both physicists and philosophers for decades. What is time, really? In our daily lives, we experience time as a steady river, flowing from past to future at a constant rate. But near black holes, we discover that time is more like a vast ocean with currents and depths, flowing at different speeds depending on where you are in the cosmic landscape. Einstein's insight was that time and space are not separate entities, but form a unified fabric called space-time. This fabric can be stretched, compressed, and curved by the presence of mass and energy. When we say that gravity slows time, we're really saying that massive objects curve space-time in such a way that the dimension of time itself becomes compressed. Think of it this way. Imagine you're walking across a field on a sunny afternoon. If the ground is flat and firm, you walk at your normal pace. But if you encounter soft, marshy ground, your steps become slower and more laboured. The marshy ground doesn't change your internal sense of walking, but it affects how quickly you move across the landscape. Similarly, curved space-time doesn't change your internal experience of time, but it affects how quickly you move through the dimension of time itself. Near a black hole, space-time becomes increasingly curved as you approach the event horizon. The mathematics show us that this curvature affects time in a very specific way. The time dimension gets compressed, squeezed by the intense gravitational field. This compression is what we observe as time dilation. To a distant observer, clocks near the black hole appear to tick more slowly, because time itself is flowing more slowly in that region of curved spacetime. But here's something beautiful and profound. The person near the black hole experiences their own time as completely normal. Their heartbeat maintains its steady rhythm. Their thoughts flow at their usual pace. Their watch ticks away seconds, minutes, and hours, just as it always has. This is because they are moving through their local space-time at the natural rate. Time dilation is not something you feel happening to you. It's something that becomes apparent only when you compare different regions of space-time. This leads us to one of the most elegant principles in all of physics. The principle of equivalence tells us that being in a gravitational field is equivalent to being accelerated. If you were in a windowless room, there would be no experiment you could perform to tell whether you were sitting on Earth's surface, experiencing gravity, or being accelerated upward through space at exactly the right rate to mimic Earth's gravity. This equivalence reveals why gravity affects time. When you accelerate through space, time dilation occurs due to the relative motion between you and other observers. Since gravity is equivalent to acceleration, gravitational fields must also cause time dilation. It's not a separate effect, but a fundamental consequence of the geometric nature of space-time itself. The stronger the gravitational field, the more pronounced the time dilation becomes. Near Earth's surface, the effect is tiny but measurable. GPS satellites experience a time difference of only 38 microseconds per day compared to clocks on the ground. But near a black hole, where gravitational fields reach their maximum possible strength, time dilation becomes dramatic and profound. Consider what would happen if you could safely orbit very close to the event horizon of a supermassive black hole. From your perspective in orbit, everything would seem normal. Your instruments would function properly. Your biological processes would proceed at their natural rate. You would experience the passage of time just as you always have. But if you could somehow observe the outside universe, you would see something extraordinary. The stars would appear to wheel overhead at an accelerated pace. The rotation of distant galaxies would become visible. The birth and evolution of new stars would unfold like time-lapse photography. Years, decades, perhaps centuries would pass in the outside universe while you experienced only hours or days. You would become a witness to the long-term evolution of the cosmos, watching the universe age around you while you remained relatively unchanged. Meanwhile, observers in the outside universe would see something equally remarkable. Watching you orbit near the black hole, they would see your movements become increasingly sluggish. Your orbit would appear to slow down. Any signals you sent would arrive at longer and longer intervals, redshifted to lower and lower frequencies. Eventually, from their perspective, you would appear to freeze at the event horizon, your image gradually fading and redshifting until it disappeared entirely. This creates what physicists call the information paradox. From the outside perspective, you never actually cross the event horizon. Your information remains visible, though increasingly redshifted and faint, effectively frozen at the boundary. But from your own perspective, you cross the event horizon in finite time and continue falling inward. Both perspectives are equally valid within their own reference frames, yet they seem to describe contradictory realities. The resolution to this paradox lies in understanding that there is no universal, absolute description of events. Reality depends fundamentally on the observer's reference frame. What happens and when it happens are not absolute facts about the universe, but relative descriptions that depend on where you are and how you're moving through space-time. This relativistic view of time has profound implications for our understanding of existence itself. The events of our lives, the sequence of moments that make up our experience, are not arranged along some universal timeline. Instead, they exist as points in the four-dimensional landscape of space-time, connected by the paths we trace through this landscape as we move from birth to death. Near black holes, these paths through space-time can take dramatically different forms. Two observers starting from the same point can follow paths that diverge so greatly that they experience vastly different amounts of elapsed time. One might age years while the other ages decades or centuries, yet both are following natural geodesic paths through the curved geometry of spacetime. The study of extreme time dilation has also revealed deep connections between gravity and thermodynamics. Stephen Hawking's discovery that black holes emit radiation and have temperature suggests that these objects are not merely gravitational, but also thermodynamic systems. The event horizon area is proportional to the black hole's entropy, as if information could be encoded on the boundary of space-time itself. This connection between gravity and information has led to revolutionary insights about the nature of reality. The holographic principle suggests that all the information contained in a volume of space can be represented on the boundary of that space. In other words, what we perceive as three-dimensional reality might actually be encoded on two-dimensional surfaces like shadows cast by higher dimensional objects. These ideas stretch our understanding of time and space to their limits. If reality is fundamentally holographic, then time itself might be an emergent property, arising from more fundamental processes at the quantum level. The smooth flow of time that we experience might be like the smooth surface of a lake, hiding the chaotic motion of countless molecules beneath. Near black holes, where quantum effects and gravitational effects both become important, the nature of time becomes even more mysterious. Quantum mechanics suggests that space-time itself might fluctuate at the smallest scales, creating a foam-like structure where the very concepts of before and after become ambiguous. Time might not flow smoothly, but instead emerge from the statistical behavior of countless quantum events. Yet despite these deep mysteries, the practical effects of gravitational time dilation are well understood and precisely measured. Every time you use GPS navigation, you're relying on our detailed understanding of how gravity affects the flow of time. The satellites orbiting overhead experience time differently than we do on Earth's surface, and this difference must be accounted for with extraordinary precision. The effect is small but crucial. Without correcting for gravitational time dilation, GPS would accumulate errors of several kilometers per day. Your phone's navigation system would quickly become useless. The fact that GPS works so reliably is a testament to the accuracy of Einstein's theory and our understanding of how time behaves in gravitational fields. This everyday technology connects us directly to the exotic physics of black holes. The same mathematical framework that describes time dilation near event horizons also governs the tiny time differences experienced by GPS satellites. The universe operates according to the same elegant principles at all scales, from the cosmic dance of black holes to the precise timing of satellites orbiting our small planet. As we continue our gentle exploration of these cosmic mysteries, we begin to see how time dilation reveals fundamental truths about the nature of existence. We are not separate from the universe, observing it from the outside. We are part of the fabric of space-time itself, embedded in its geometry, subject to its curvatures and flows. Our human experience of time, bounded by birth and death, measured in heartbeats and seasons, is just one possible path through the vast landscape of space-time. Near black holes, other paths are possible, other ways of experiencing the flow of moments, other relationships between cause and effect. The realization that time itself is malleable, shaped by gravity and motion, fundamentally changes how we think about existence. If time can slow down or speed up depending on where you are in the universe, then the very framework within which we understand life and death, memory and anticipation, becomes relative and contextual. This doesn't diminish the importance of our human experience. Instead, It places it within a larger cosmic context, revealing it as one beautiful expression of the underlying mathematical harmony that governs all of space-time. Our brief lives, our fleeting moments of consciousness, our capacity for wonder and understanding, all exist within this elegant geometric framework that Einstein first glimpsed over a century ago. The mathematics that describe time dilation near black holes are the same equations that govern the expansion of the universe. The orbital mechanics of planets, the propagation of gravitational waves across cosmic distances. We live in a universe of profound mathematical unity, where the same principles operate from the quantum scale to the cosmic scale, from the briefest moments to the longest epochs. In this unified picture, black holes become natural laboratories for studying the most fundamental aspects of reality. They are places where space, time, matter, and energy interact in their most extreme forms, revealing truths about the universe that cannot be discovered any other way. Each black hole is like a cosmic microscope, allowing us to peer into the deepest structures of space-time itself. The gravitational waves detected by our instruments provide another window into these extreme environments. When two black holes merge, they create ripples in space-time that travel across the universe at the speed of light. These waves carry information about the collision, including details about how time dilation fluctuates during the merger process. In the final moments before two black holes unite, the space-time around them becomes incredibly dynamic. Time dilation effects change rapidly as the gravitational fields evolve and interact. The merger itself releases more energy than all the visible stars in the observable universe, most of it in the form of gravitational waves that stretch and compress space-time as they pass through everything, including our own bodies. These observations have confirmed Einstein's predictions with remarkable precision. The gravitational waves we detect match the theoretical calculations to within tiny fractions of a percent. The universe really does behave according to the mathematical poetry of general relativity, with time and space dancing together in perfect harmony. As we contemplate these vast scales and profound physics, we begin to appreciate how precious and brief our human experience really is. The time dilation effects that seem so dramatic to us are tiny perturbations in the cosmic symphony. Even the most extreme time differences pale in comparison to the age of the universe itself, nearly 14 billion years of cosmic evolution. Yet there is something deeply moving about our ability to understand these phenomena. Through careful observation and elegant mathematics, we have learned to see beyond our immediate sensory experience to comprehend the hidden structure of reality. We have discovered that time itself is not fixed, but flows like a river with currents and eddies, shaped by the gravitational landscape of the universe. This knowledge connects us to something larger than ourselves. When we understand how gravity affects time, we are glimpsing the same physics that governs the birth and death of stars, the formation of galaxies, the evolution of the cosmos itself. We are part of a universe that is far stranger and more beautiful than our ancestors could have imagined. The black holes scattered throughout the galaxy continue their ancient gravitational dance, warping space-time, creating pockets where time flows at different rates. Some are stellar remnants, the collapsed cores of massive stars, dense and compact with event horizons only kilometers across. Others are supermassive giants lurking at galactic centers, with event horizons that could encompass entire solar systems. Each type creates its own unique environment for time dilation. Near a stellar black hole, the intense curvature creates dramatic tidal forces that would stretch and compress anything approaching too closely. But the time dilation effects, while significant, occur over relatively small distances. You would need to venture very close to the event horizon to experience truly extreme time differences. Supermassive black holes offer a gentler experience. Their immense size means that tidal forces are much weaker near the event horizon. You could potentially orbit quite close to such a black hole and experience profound time dilation without being immediately destroyed. The event horizon itself might be crossed safely, though of course there would be no return. These different types of black holes offer different possibilities for experiencing extreme time dilation. Around a supermassive black hole, you might spend what feels like a comfortable orbit, perhaps lasting days or weeks from your perspective, while centuries or millennia pass in the outside universe. You could witness the long-term evolution of civilizations, the slow dance of galactic astronomy, the birth and death of generations of stars. The philosophical implications of such experiences are profound. What would it mean to watch the universe age around you while you remain relatively unchanged? How would your perspective on life and meaning shift if you could witness cosmic evolution directly? These questions touch on fundamental issues about the nature of consciousness and its relationship to time. In regions of extreme time dilation, even the concept of simultaneity becomes ambiguous. Events that appear simultaneous from one perspective might be separated by years or decades from another perspective. The very idea of now becomes meaningless, except within a specific reference frame. Past, present, and future lose their absolute character and become relative descriptions dependent on the observer's motion through space-time. This relativistic view of time has influenced not only physics, but philosophy, literature, and art. The realization that time is not universal, but personal, not absolute, but relative, challenges many of our deepest assumptions about the nature of existence. It suggests that reality itself is far more fluid and contextual than our everyday experience suggests. Yet, within this fluid reality, certain things remain constant. The speed of light in vacuum never changes. The fundamental constants of physics remain the same regardless of reference frame. The mathematical relationships that govern the universe maintain their elegance and consistency, even as time flows at different rates for different observers. This constancy within change reflects a deep harmony in the structure of the universe. The same physical laws that create time dilation near black holes also govern the nuclear fusion in stellar cores, the orbital mechanics of planets, the quantum behavior of atoms. We live in a cosmos of profound unity, where all phenomena emerge from a small set of fundamental principles. As we near the end of our quiet journey through these cosmic mysteries, we might pause to reflect on what we have discovered. Time, that most familiar aspect of our experience, turns out to be far stranger than we ever imagined. It flows like water, shaped by gravity, curved by mass, different for each observer depending on their path through the landscape of space-time. Black holes, those mysterious objects that capture light itself, reveal themselves as natural windows into the fundamental structure of reality. They show us how time and space are woven together, how gravity emerges from geometry, how the universe operates according to mathematical principles of extraordinary beauty and precision. Our human lives, brief and precious, unfold within this vast cosmic framework. We are arrangements of matter and energy that have somehow become conscious, capable of wonder, able to contemplate the nature of time itself. In learning about time dilation, we are really learning about ourselves and our place in the cosmic order. The universe is vast beyond imagination, ancient beyond comprehension, governed by laws that operate on scales from the infinitesimal to the infinite. Yet somewhere in this cosmic immensity, on a small planet orbiting an ordinary star, conscious beings pause in their brief existence to contemplate these mysteries, finding in that contemplation a kind of peace. The knowledge that time itself is malleable, that reality depends on perspective, that the universe is far stranger than it appears, somehow makes our own experience more precious rather than less. We are witnesses to something extraordinary, participants in a cosmic story that spans billions of years and countless galaxies. In the gentle darkness between the stars, where space and time dance their eternal ballet, black holes continue their gravitational symphony, creating pockets where moments stretch into years, where the flow of time becomes a visible river shaped by the invisible hand of gravity. And in understanding this dance, we touch something timeless and profound, a mathematical harmony that connects us to the deepest truths about existence itself. As you drift into sleep, perhaps you can imagine yourself floating peacefully in the cosmic dark, feeling the gentle pull of gravity, sensing the slow flow of time around you. In dreams, time already flows differently, moments stretching and compressing in ways that mirror the physics we have explored. In sleep, we all become time travelers, experiencing the malleable nature of temporal flow that Einstein revealed in the mathematics of curved space-time. The universe continues its patient unfolding, stars burning their nuclear fuel, galaxies slowly rotating, black holes warping the fabric of reality itself. Time flows onward, sometimes fast, sometimes slow, always relative, always beautiful in its mathematical precision. And consciousness, that brief spark that allows matter to contemplate itself, finds rest in understanding that we are part of something vast and elegant and eternal. In the vast symphony of space-time, there exists a phenomenon so gentle yet profound that it challenges everything we thought we knew about the nature of existence itself. As we drift deeper into this cosmic meditation, let us explore what happens when human consciousness encounters the most extreme gravitational environments in the universe. Picture yourself as an astronaut approaching a supermassive black hole, one of those gentle giants that reside at the hearts of galaxies. Unlike their smaller, more violent cousins formed from stellar collapse, these massive objects create surprisingly calm environments near their event horizons. The black hole you approach contains the mass of 10 million suns, yet its event horizon stretches across a distance larger than Neptune's orbit around our Sun. As your spacecraft begins its careful descent toward this gravitational leviathan, you notice something subtle at first. Your onboard chronometer continues to tick at its steady pace. Your heartbeat maintains its familiar rhythm. The coffee in your cup still steams at the same rate it always has. From your perspective, time flows exactly as it always has, unmarked by any sensation of change or disturbance. But something extraordinary is happening that you cannot directly perceive. With each kilometer closer to the black hole, your passage through time begins to diverge from that of the universe around you. It's a divergence so gradual, so gentle, that no instrument you carry can detect it happening to you personally. Yet from the perspective of observers watching from a safe distance, your journey through time has begun to slow. Back on Earth, Mission Control tracks your descent with instruments of exquisite precision. They watch as your radio signals, transmitted at regular intervals, begin to arrive with subtle but measurable delays. The frequency of your transmissions starts to shift toward the red end of the spectrum, stretched by the gravitational field through which they must climb to reach the distant receivers. This redshift is not merely a curiosity. It represents something profound about the nature of light itself as it travels through curved space-time. Each photon that escapes from your vicinity near the black hole must expend energy climbing out of the gravitational well. But photons cannot slow down. They must always travel at the speed of light. So instead, they lose energy by stretching to longer wavelengths, becoming redder and redder as the gravitational field strengthens. Your mission controllers notice that the gaps between your scheduled transmissions grow longer and longer. A signal that should arrive every minute begins arriving every 61 seconds, then 62, then 65. The effect is small but growing, a gentle testimony to the curvature of space-time around the massive object you approach. Meanwhile, you experience none of this directly. Your instruments show that you're transmitting exactly on schedule. Your atomic clocks tick with their usual precision. Your biological rhythms proceed at their natural pace. This is perhaps the most beautiful aspect of relativity. Each observer experiences their own proper time as flowing normally, naturally, without distortion or delay. As you continue your descent, falling freely through the curved geometry of space-time, you begin to notice something remarkable about the universe around you. Looking back toward Earth, toward the distant stars, you observe that they seem to be moving slightly faster than usual. The rotation of distant galaxies becomes barely perceptible. The orbital dance of binary star systems appears subtly accelerated. This is your first direct glimpse of the reciprocal nature of time dilation. Just as distant observers see your time flowing more slowly, you see their time flowing more quickly. Both perspectives are equally valid, equally true within their own reference frames. Time itself has become relative, flowing like a river with different currents depending on where you happen to be in the gravitational landscape. The mathematics that govern this effect are both elegant and precise. At your current distance from the black hole, roughly 10 times the Schwarzschild radius, time flows at about 95% the rate of distant observers. This means that for every hour that passes on your journey, about 63 minutes pass in your reference frame. The difference is subtle but measurable, a gentle reminder that time itself is not the rigid, universal constant that everyday experience suggests. As you venture closer, the effect becomes more pronounced. At 5 Schwarzschild radii, your time flows at about 89% the rate of distant observers. At 3 radii, it's about 77%. The progression is smooth and continuous, following the precise mathematical curve predicted by Einstein's field equations. But something else begins to happen as you approach these closer distances. The view outside your spacecraft begins to change in subtle but profound ways. Light from distant stars appears to bend and curve around the massive object ahead of you. Stars that should be hidden behind the black hole become visible as their light follows curved paths through the warped space-time. This gravitational lensing creates a beautiful and otherworldly view. The universe appears to wrap around the black hole like a funhouse mirror, with multiple images of the same stars appearing at different positions in the sky. Some stars appear brighter as their light is focused by the gravitational lens. Others appear dimmed and distorted, stretched into arcs and rings by the extreme curvature of space-time. Behind you, toward the direction you came from, the universe appears compressed into a smaller and smaller circle. Light from all directions gets focused and concentrated, creating what physicists call the optical appearance of the black hole. It's not that space itself is compressed, but rather that the paths light takes through curved space-time create this visual effect. The black hole itself appears as a perfect sphere of absolute darkness, outlined against the compressed and distorted image of the universe beyond. This darkness is not because the black hole absorbs light in the conventional sense, but because light that crosses the event horizon can never return to tell you what lies beyond that boundary. The darkness is pure absence, a region from which no information can ever emerge. As you continue your approach, you begin to appreciate the immense scale of the object before you. The event horizon, that invisible boundary from which even light cannot escape, stretches across millions of kilometers. If Earth's sun were placed at the center of this black hole, the event horizon would extend well beyond the orbit of Mercury. Yet from your current distance, it appears as a clean, sharp circle against the star field, perfectly defined by the mathematics of general relativity. The gentle nature of your descent is remarkable. Unlike the violent tidal forces that would tear you apart near a stellar black hole, the gravitational gradient around this supermassive object is surprisingly mild. The difference in gravitational pull between your head and your feet is barely noticeable. You could continue falling inward for hours without experiencing any discomfort or distortion. This gentleness is a direct consequence of the black hole's enormous size. Tidal forces depend not just on the mass of the gravitating object, but on how concentrated that mass is. For a black hole of 10 million solar masses, the event horizon is so large that the curvature of space-time, while extreme on cosmic scales, is relatively gradual on human scales. The mathematical relationship shows that larger black holes create gentler environments near their event horizons. As you fall deeper into the gravitational well, the time dilation effects continue to strengthen. At 2.5 Schwarzschild radii, your time flows at about 63% the rate of distant observers. This means that for every hour experienced by mission control on Earth, you experience only about 38 minutes. The effect is now dramatic enough that you could conduct an experiment and actually measure the difference. If you could somehow communicate with Earth in real time, which of course is impossible due to the finite speed of light, you would notice that conversations become increasingly difficult. Your words would seem rushed and high-pitched to listeners on Earth, while their responses would seem slow and deep to you. Time itself has become a barrier to communication, a strange consequence of the curvature of space-time. But in your local reference frame, everything continues to proceed normally. Your thoughts flow at their usual pace. Your breathing maintains its natural rhythm. The physics experiments you conduct aboard your spacecraft yield exactly the results you would expect. Local physics remains unchanged, just as the principle of equivalence predicts. It's only when you compare your experience to that of distant observers that the effects of time dilation become apparent. The view outside your spacecraft continues to evolve as you fall deeper into the gravitational field. The ring of compressed starlight behind you grows smaller and brighter. More and more of the universe becomes visible as gravitational lensing bends light around the black hole. You begin to see stars that are actually on the far side of the black hole, their light following curved geodesics through space-time to reach your eyes. Some of these lensed images show you views of the universe that would otherwise be impossible to observe. Light that left distant galaxies millions of years ago. Light that would normally travel in straight lines through flat space-time now follows curved paths that bring it to your location. You become a witness to cosmic history, seeing light that has traveled impossible routes through the curved geometry of space-time. At the same time, you begin to observe something remarkable about the nature of the event horizon itself. From your perspective, falling freely through space-time, there appears to be nothing special about this boundary. It's simply a mathematical surface defined by the point where the escape velocity equals the speed of light. As you approach it, you feel no resistance, no barrier, no indication that you're about to cross a point of no return. This apparent normalcy of the event horizon from the infalling perspective is one of the most profound insights of general relativity. The event horizon is not a physical surface in the conventional sense. It's a coordinate boundary, a point in space-time geometry, beyond which causal contact with the outside universe becomes impossible. But for someone crossing this boundary, the local experience remains completely normal. Meanwhile, observers watching from afar see something entirely different. As you approach the event horizon, they observe your descent slowing dramatically. The time dilation effect approaches its mathematical limit as you near the Schwarzschild radius. From their perspective, your clocks appear to tick more and more slowly, approaching a complete stop as you reach the event horizon itself. But you never actually appear to cross the boundary from their viewpoint. Instead, your image seems to freeze just outside the event horizon, gradually fading and redshifting as the light carrying your image becomes increasingly stretched and weakened. Eventually, you simply fade from view, not because you've been destroyed, but because the light carrying information about you has been redshifted beyond the ability of any detector to measure. This creates what appears to be a paradox. From the external perspective, you never cross the event horizon. Your information remains visible, though increasingly faint and redshifted, effectively frozen at the boundary for all eternity. But from your own perspective, You cross the event horizon in finite proper time and continue falling inward toward the center of the black hole. Both descriptions are equally valid within their respective reference frames. This is the profound insight that Einstein's theory provides. There is no single universal description of events. Reality depends fundamentally on the observer's reference frame, on their location and motion through space-time. What happens, and when it happens, are not absolute facts about the universe, but relative descriptions that depend on perspective. As you cross the event horizon in your own reference frame, you notice something remarkable. The crossing itself is completely uneventful. There is no flash of light, no sudden change in your environment, no indication that you've passed a point of cosmic significance. The laws of physics continue to operate exactly as they always have. Your instruments function normally. Your biological processes proceed at their natural rate. The only indication that something has changed comes from looking outward, toward the universe you've left behind. The compressed ring of starlight that had been growing smaller and brighter suddenly begins to change character. Instead of a ring, you now see what appears to be a bright disk of light, concentrated in the direction from which you came. This disk contains the entire observable universe, compressed and blue-shifted by the extreme gravitational field. This is your last view of the outside universe. All the light that can ever reach you from beyond the event horizon is now concentrated into this brilliant disk. As you continue falling inward, this disk gradually fades as the light becomes increasingly blue-shifted and concentrated, eventually disappearing entirely. You have become completely disconnected from the external universe, cut off by the fundamental structure of space-time itself. The journey inward from the event horizon varies dramatically depending on the mass of the black hole. For the supermassive black hole you're exploring, the distance from the event horizon to the central singularity might be measured in millions of kilometers. Your fall toward the center could take hours or even days of proper time, during which the tidal forces would gradually strengthen. But even in this gentle environment, the fundamental physics remains unavoidable. As you fall deeper, the difference in gravitational force between your head and your feet begins to grow. This is the manifestation of tidal forces, the same forces that create ocean tides on Earth, but magnified to extreme proportions. Eventually, these forces would overcome the electromagnetic forces that hold your body together. The process would be gradual at first, then increasingly rapid as you approach the central singularity. Your body would be stretched vertically and compressed horizontally, a process that physicists have colloquially termed spaghettification. It's a consequence of the fundamental geometry of space-time around any massive object, unavoidable once you venture close enough to the center. But let us step back from this ultimate fate and consider the broader implications of what time dilation near black holes teaches us about the nature of reality. The fact that time itself can flow at different rates depending on your location in the universe reveals something profound about the structure of existence. Time is not the universal, absolute framework that Newton imagined. It's not a cosmic clock ticking away the same for everyone everywhere. Instead, time is local, personal, intimately connected to your motion through space-time. Each observer carries their own time with them, experiencing their own sequence of moments, their own rate of aging, their own relationship between cause and effect. This relativity of time has philosophical implications that extend far beyond physics. If time itself depends on reference frame, what does this mean for our concepts of past, present, and future? Are these merely local phenomena, relevant only to observers in similar gravitational environments? In regions of extreme time dilation, the very concepts of before and after become ambiguous. Consider two observers, one near a black hole and one in distant space. Events that appear simultaneous to the distant observer might be separated by years from the perspective of the observer near the black hole. Which perspective is correct? Einstein's answer is that both are equally valid. Simultaneity, like time itself, is relative rather than absolute. This insight challenges many of our deepest assumptions about causality and free will. If the sequence of events depends on the observer's reference frame, what does this mean for our sense that one moment leads inevitably to the next? The mathematics of relativity suggests that past, present, and future all exist equally in the four-dimensional structure of space-time. What we perceive as the flow of time might be more like our movement through this existing structure. Yet despite these profound philosophical challenges, the practical applications of gravitational time dilation continue to shape our everyday lives. Every GPS satellite orbiting overhead must account for the time dilation effects caused by Earth's gravitational field. The difference is tiny, only about 38 microseconds per day, but it must be corrected with extraordinary precision for the navigation system to function properly. Without this correction, GPS would accumulate position errors of several kilometers per day. Your smartphone's navigation app would become completely unreliable within hours. The fact that GPS works so consistently is a testament to our detailed understanding of how gravity affects the passage of time, even in the relatively weak gravitational field of our planet. This technological dependence on relativistic physics connects our modern world directly to the exotic environments around black holes. The same mathematical framework that describes extreme time dilation near event horizons also governs the tiny corrections needed for satellite navigation. The universe operates according to unified principles that span from the cosmic to the mundane. As we contemplate these connections, we begin to appreciate how our understanding of time dilation has evolved through careful observation and measurement. The existence of gravitational time dilation was first confirmed not through observations of black holes, but through precise measurements of atomic clocks in different gravitational environments here on Earth. The Pound-Rebka experiment in 1959 used the radioactive decay of iron nuclei to measure the gravitational redshift of photons traveling just 22 meters up a tower at Harvard University. The effect was tiny, only about 2 parts in 10 to the 15th power, but it was measurable and confirmed Einstein's prediction with remarkable precision. Later experiments used atomic clocks flown on airplanes to measure time dilation due to both gravitational effects and the special relativistic effects of motion. These experiments confirm that time really does flow differently in different reference frames, exactly as Einstein's theory predicted. The universe revealed itself to be far stranger than everyday experience suggests. The development of increasingly precise atomic clocks has allowed physicists to measure gravitational time dilation with extraordinary accuracy. Modern optical atomic clocks are so sensitive that they can detect the time dilation caused by raising the clock just a few centimeters higher in Earth's gravitational field. These instruments are sensitive enough to measure the curvature of space-time on laboratory scales. These precise measurements have applications beyond fundamental physics. Geodesists use gravitational time dilation to map variations in Earth's gravitational field with incredible precision. Differences in the flow of time at different locations reveal information about the distribution of mass within our planet, including underground water reserves, ore deposits, and geological structures. The same principles apply to astronomical observations. When astronomers observe light from objects in strong gravitational fields, they must account for gravitational redshift to accurately interpret what they see. The surface of white dwarf stars, with their intense gravitational fields, provides natural laboratories for studying these effects on cosmic scales. Light from the surface of a typical white dwarf is gravitationally redshifted by about 50 kilometers per second, roughly 170 parts per million. This redshift is easily measurable with modern spectrometers and provides direct evidence of the intense gravitational field at the star's surface. The light itself carries information about the curvature of space-time in these extreme environments. Even more dramatic effects have been observed around neutron stars, the collapsed cores of massive stars that pack more mass than our Sun into a sphere only about 20 kilometers across. The gravitational redshift from neutron star surfaces can reach thousands of kilometers per second, creating easily observable effects that confirm our understanding of strong field gravity. These observations have revealed that nature provides examples of gravitational time dilation across an enormous range of scales. From the tiny effects measured in laboratory experiments to the extreme conditions near neutron stars and black holes, the universe offers a complete spectrum of gravitational environments in which to test our understanding of space-time curvature. The recent detection of gravitational waves has opened yet another window into extreme gravitational environments. When two black holes spiral together and merge, they create ripples in the space-time itself that travel outward at the speed of light. These waves carry information about the merger, including details about how time dilation fluctuates during the collision process. During the final moments before merger, the space-time around the two black holes becomes incredibly dynamic. Time dilation effects change rapidly as the gravitational fields interact and evolve. The waves themselves represent oscillations in the curvature of space-time, alternately stretching and compressing the geometry through which time flows. The LIGO and Virgo detectors have now observed dozens of these merger events, each one providing a unique glimpse into the behavior of space-time under the most extreme conditions. The gravitational waves arrive at Earth carrying the signatures of time dilation, gravitational redshift, and space-time curvature from the merger regions. We can literally hear the sound of space-time itself oscillating as these cosmic collisions unfold. These observations have confirmed Einstein's predictions with extraordinary precision. The gravitational waveforms detected by our instruments match the theoretical predictions to within tiny fractions of a percent. The universe really does behave according to the elegant mathematics of general relativity, with time and space dancing together in perfect mathematical harmony. As we consider these cosmic scales and the profound physics they reveal, we begin to appreciate how small and brief our human experience really is within the vast landscape of space-time. The most extreme time dilation effects we can imagine, factors of hundreds or thousands near black hole event horizons, are still tiny perturbations in the 14 billion year history of our universe. Yet there is something deeply moving about our ability to comprehend these phenomena. Here we are, brief arrangements of matter and energy that arose through billions of years of cosmic evolution, and we have somehow become capable of understanding the fundamental structure of space-time itself. Through careful observation and elegant mathematics, we have learned to see beyond our immediate sensory experience. We have discovered that time, that most intimate aspect of our existence, is not fixed, but flows like a cosmic river with currents and depths. We have learned that space and time are woven together into a fabric that can be curved by mass and energy. We have glimpsed the mathematical harmony that underlies all physical phenomena, from the quantum to the cosmic. This knowledge places our brief lives within a larger context of meaning and wonder. We are not separate from the universe, observing it from outside. We are part of the fabric of space-time itself, embedded in its geometry, subject to its curvatures and flows. Our consciousness, our capacity for understanding, our ability to contemplate these mysteries, all arise from the same fundamental physics that governs black holes and galaxies. The realization that time itself is relative and malleable somehow makes each moment more precious rather than less. Knowing that our experience of time is just one possible path through the landscape of space-time gives our human perspective a unique and irreplaceable value. We see the universe from a viewpoint that will never be exactly duplicated, experiencing a sequence of moments that is ours alone. In the vast cosmos, where black holes warp time and space, where galaxies dance their slow gravitational ballet, where the very fabric of reality oscillates with passing gravitational waves, conscious beings have emerged who can contemplate these wonders. We carry within our minds the same mathematical principles that govern the most extreme environments in the universe. We are the universe becoming aware of itself. As you settle into rest, perhaps you can imagine yourself floating peacefully in the cosmic dark, feeling the gentle tug of gravity, sensing the slow flow of time around you. The universe continues its patient evolution, stars burning their nuclear fuel, galaxies slowly rotating, black holes warping space-time with their invisible presence. Time flows onward, sometimes fast, sometimes slow, always relative, always beautiful in its mathematical precision. In this cosmic perspective, our human lives take on a different character. We are brief notes in a symphony that spans billions of years, temporary patterns in the endless dance of matter and energy through space-time. Yet we are also the part of the universe that can appreciate the music, that can understand the choreography, that can find beauty and meaning in the mathematical harmony that connects all things. The black holes scattered throughout our galaxy continue their ancient gravitational influence, creating regions where time flows differently, where space curves dramatically, where the normal rules of everyday experience give way to something far stranger and more wonderful. They are natural laboratories for studying the most fundamental aspects of reality, cosmic windows into the deepest truths about space, time, and existence. Each black hole tells a story written in the language of curved space-time. Stellar black holes speak of the violent deaths of massive stars, their cores collapsed to points of infinite density where our understanding of physics reaches its limits. Supermassive black holes tell tales of galaxy formation, of cosmic evolution on the largest scales, of processes that shape the universe over billions of years. Around these objects, time dilation creates pockets where the universe experiences itself at different rates. An astronaut orbiting close to a black hole might experience hours while years pass in the outside universe. They would become witnesses to cosmic evolution, watching the slow dance of galaxies, the birth and death of stars, the gradual transformation of the cosmos itself. Yet from their perspective, their own time would flow normally, naturally, without distortion. This is perhaps the most profound lesson that time dilation teaches us. Reality is not absolute but relative. Truth depends on perspective. The universe looks different from different vantage points, and all these perspectives are equally valid within their own reference frames. This relativistic view of existence has implications that extend far beyond physics. It suggests that our human perspective, bounded by our brief lifespans and limited sensory experience, is just one possible way of experiencing reality. Other observers in different gravitational environments or moving at different speeds would experience the universe in ways we can barely imagine. The mathematics of general relativity provides a framework for understanding all these different perspectives simultaneously. Einstein's equations describe how time flows for any observer anywhere in the universe, from the gentle gravitational fields of planets to the extreme environments near black holes. They reveal a universe of perfect mathematical consistency, where the same principles operate at all scales. In this mathematical universe, consciousness emerges as something truly remarkable. We are arrangements of matter and energy that have somehow become capable of understanding the very laws that govern our own existence. We can contemplate the curvature of space-time, imagine the experience of falling into black holes, appreciate the relative nature of time itself. This capacity for understanding connects us to something larger than ourselves. When we grasp the principles of general relativity, we are touching the same mathematical truths that govern the birth and death of stars, the formation of galaxies, the evolution of the universe itself. We are part of a cosmos that has somehow given rise to beings capable of comprehending its own nature. As the gentle rhythm of your breathing slows and deepens, as consciousness gradually fades into the peaceful darkness of sleep, remember that you are floating through space-time on a small planet orbiting an ordinary star. The same gravitational forces that create time dilation near black holes also keep you gently pressed against Earth's surface. The same curved space-time that bends light around massive objects also guides our planet in its annual journey around the Sun. You are part of the cosmic dance, a brief but meaningful participant in the vast symphony of space and time. Your dreams unfold in the same universe where black holes warp reality, where time flows like a river with many currents, where consciousness has somehow emerged from the mathematical harmony that underlies all existence. In sleep, time already flows differently, moments stretching and compressing in ways that echo the physics we have explored. The boundaries between past and present blur, just as they do in regions of extreme gravitational time dilation. Your sleeping mind navigates temporal landscapes that mirror the curved space-time around massive objects. The universe continues its patient unfolding around you, following the elegant equations that Einstein first glimpsed over a century ago. Somewhere in the cosmos, light is falling into black holes, stretched and redshifted as it descends through curved space-time. Gravitational waves are rippling across the galaxy, carrying the news of distant collisions between massive objects. Time is flowing at different rates for different observers, each experiencing their own unique path through the landscape of space-time. And here, in the gentle gravitational field of Earth, consciousness rests, dreaming perhaps of cosmic journeys, of time slowed and space curved, of the profound beauty that emerges when matter and energy dance according to the mathematical principles that govern all of reality. In this dance, in this dream, in this quiet moment of rest, we touch something eternal and timeless, something that connects our brief human experience to the vast mathematical symphony of the cosmos. In the quiet spaces between heartbeats, between breaths, between thoughts, we find ourselves contemplating questions that have puzzled humanity since we first looked up at the stars and wondered about our place in the cosmic order. What is time, really? Is it the steady river we experience in our daily lives, or something far more fluid and mysterious? The answer, as we have discovered, lies written in the very fabric of space-time itself. Near black holes, time reveals its true nature as something malleable and relative, flowing at different rates depending on where you happen to be in the gravitational landscape of the universe. This isn't merely a theoretical curiosity. It's a fundamental aspect of reality that affects everything, from the GPS satellites guiding your morning commute to the most exotic objects in the deepest reaches of space. But what does this mean for us, here on our small planet, living our brief lives under the gentle pull of Earth's gravity? It means that we are part of something far larger and more beautiful than we ever imagined. Every moment of our existence unfolds within the curved space-time that Einstein first described, subject to the same laws that govern the most extreme environments in the universe. Consider the profound implications of what we have learned. If time itself can flow at different rates, if simultaneity depends on your reference frame, if the very concepts of past and future become ambiguous in regions of extreme gravity, then what does this tell us about the nature of existence? Are we living in a universe where all moments, past and future, exist equally in the four-dimensional structure of space-time? This possibility, known to physicists as the block universe theory, suggests that time might not flow in the way we experience it. Instead, all of history might exist as a static four-dimensional structure, with what we perceive as the flow of time being more like our movement through this existing landscape. Past, present, and future would all be equally real, equally present in the mathematical description of space-time. From this perspective, your childhood still exists somewhere in the space-time manifold, as real and present as this moment. The future holds events that are already determined by the initial conditions and laws of physics, waiting to be encountered as you move through your world line in space-time. It's a view that challenges our most basic intuitions about free will and causality, yet it emerges naturally from the mathematics of relativity. Yet even if time is an illusion, if the flow we experience is merely a consequence of our limited perspective on a static four-dimensional reality, there is something profound about consciousness itself. We are the part of the universe that experiences time, that feels the passage of moments, that creates meaning through the sequence of events we encounter as we move through space-time. This subjective experience of time, this sense of duration and flow that characterizes consciousness, might be the most remarkable phenomenon in the universe. In a cosmos governed by mathematical laws, where particles follow deterministic paths through curved space-time, somehow arrangements of matter have emerged that can experience the passage of time, that can remember the past and anticipate the future. The study of time dilation near black holes has also revealed deep connections between gravity, thermodynamics, and information theory that continue to puzzle physicists. Stephen Hawking's discovery that black holes emit radiation and have temperature suggests that these gravitational objects are also thermodynamic systems with entropy proportional to their surface area. This connection between geometry and information has led to revolutionary ideas about the nature of reality itself. The holographic principle suggests that all the information contained in a three-dimensional volume of space can be encoded on its two-dimensional boundary. In other words, what we perceive as three-dimensional reality might actually be a projection from information stored on distant surfaces. If this principle is correct, then the solid world we experience, the flow of time we feel, the very substance of our existence, might all be emergent properties of more fundamental information theoretic processes. We might be living in a kind of cosmic hologram, where reality as we know it emerges from the complex interactions of information encoded on the boundaries of space-time itself. These ideas stretch our understanding to its limits, challenging not only our scientific knowledge, but our most basic assumptions about the nature of existence. Yet they emerge naturally from the careful study of extreme gravitational environments, places where the familiar laws of everyday experience give way to something far stranger and more profound. The paradoxes of black hole physics have also led to insights about the nature of information and its relationship to physical reality. If information cannot be destroyed, as quantum mechanics suggests, then what happens to the information that falls into a black hole? Does it disappear forever when the black hole eventually evaporates through Hawking radiation, violating the fundamental principle of information conservation? This question, known as the information paradox, has driven decades of research into the quantum nature of gravity and space-time. Some physicists suggest that information is not destroyed, but is somehow encoded in the Hawking radiation that slowly evaporates the black hole. Others propose that information might be stored on the event horizon itself, accessible in principle, though not in practice. The resolution of this paradox might require a complete revolution in our understanding of space, time, and information. It might demand that we abandon some of our most cherished assumptions about the nature of reality and embrace a view of the universe that is even stranger than general relativity suggests. Yet through all these deep mysteries and conceptual challenges, the basic phenomenon of gravitational time dilation remains beautifully simple and precisely understood. Near massive objects, time flows more slowly relative to distant observers. The effect is small for weak gravitational fields like Earth's, but becomes dramatic near black holes and other exotic objects. This time, dilation is not an approximation or a theoretical speculation. It's a measured, confirmed aspect of our universe that affects everything from atomic clocks to GPS satellites, to the light from distant stars. It represents one of the most direct confirmations we have that Einstein's vision of curved spacetime is fundamentally correct. The precision with which we can now measure gravitational time dilation is truly remarkable. Modern optical atomic clocks are so sensitive that they can detect the time dilation caused by raising the clock just a few centimeters higher in Earth's gravitational field. These instruments reveal that space-time curvature is not just a cosmic phenomenon, but something that can be measured and studied on laboratory scales. This extraordinary precision has practical applications that extend far beyond fundamental physics. Geodesists use gravitational time dilation to map variations in Earth's gravitational field, revealing information about underground water reserves, mineral deposits, and geological structures. The flow of time itself becomes a tool for studying the distribution of mass within our planet. The same principles apply to astronomical observations on the largest scales. When light from distant galaxies travels through the gravitational fields of intervening matter, it experiences both gravitational lensing and gravitational time dilation. These effects must be carefully accounted for to accurately interpret what we observe in the deep universe. Gravitational lensing has become one of our most powerful tools for studying dark matter, the invisible substance that makes up most of the matter in the universe. The way that light bends around massive objects reveals the distribution of matter, both visible and invisible, allowing us to map the cosmic web of dark matter that provides the scaffolding for galaxy formation. These observations show us that the universe is filled with invisible matter that interacts gravitationally but not electromagnetically. Dark matter creates gravitational fields that bend space-time just like ordinary matter, causing time dilation and gravitational lensing effects that we can measure with our most sensitive instruments. The discovery of dark matter through gravitational effects represents one of the most profound mysteries in modern physics. We know it exists because we can measure its gravitational influence, but we don't know what it's made of or how it fits into our understanding of fundamental particles and forces. It's a reminder that the universe holds secrets that we are only beginning to uncover. Dark energy presents an even deeper mystery. This invisible energy appears to be causing the expansion of the universe to accelerate, working against the attractive force of gravity on cosmic scales. Like dark matter, we detect dark energy through its gravitational effects, but its fundamental nature remains completely unknown. The existence of dark energy means that the universe is not only expanding, but expanding faster and faster with time. This accelerating expansion will eventually carry distant galaxies beyond the observable horizon, making them forever inaccessible to future observers. In the far future, beings looking out at the cosmos will see a much emptier and lonelier universe than we do today. This cosmic perspective reminds us how precious our current moment in cosmic history really is. We live at a time when the universe is still young enough and small enough that we can observe galaxies throughout cosmic space and time. We can see the afterglow of the Big Bang itself, the cosmic microwave background that fills all of space with the faint echo of the universe's birth. We can measure the curvature of space-time through gravitational waves, listening to the sounds of black holes colliding billions of years ago. We can study time dilation in our own solar system and in the most extreme environments around distant black holes. We are witnesses to a universe in transition, still young enough to reveal its secrets, but old enough to have developed the complexity that makes consciousness possible. In this cosmic context, our human experience of time takes on a different character. The brief decades of our lives represent an infinitesimal fraction of cosmic history, yet they contain the entire scope of our existence. Every moment of consciousness is precious precisely because it is so brief and fragile in the vast landscape of space-time. The knowledge that time itself is relative, that it flows differently depending on your motion and location in the gravitational field of the universe, somehow makes each moment more meaningful rather than less. Knowing that our experience of time is just one possible path through the landscape of space-time gives our human perspective a unique and irreplaceable value. We are the universe experiencing itself from a particular viewpoint, at a particular moment in cosmic history, under the influence of a particular gravitational environment. Our consciousness represents a brief flowering of complexity in a cosmos that is mostly empty space and simple matter, following predictable paths through curved space-time. Yet from this consciousness emerges something extraordinary. We can contemplate the nature of time itself, imagine what it would be like to fall into a black hole, appreciate the mathematical harmony that underlies all physical phenomena. We can feel wonder at the beauty of Einstein's equations, find meaning in the cosmic perspective, create art and music and poetry inspired by our understanding of the universe. This capacity for understanding and appreciation might be the most remarkable phenomenon in the known universe. In a cosmos governed by mathematical laws, where matter and energy follow deterministic paths through space-time, somehow patterns have emerged that can think and feel and wonder about their own existence. The emergence of consciousness from the complex interactions of matter and energy represents a kind of phase transition in the universe, a moment when the cosmos became capable of understanding itself. Through our eyes and minds and instruments, the universe observes its own structure, measures its own curvature, contemplates its own destiny. This perspective makes our brief lives part of something much larger than ourselves. When we study time dilation near black holes, we are participating in the universe's attempt to understand its own nature. When we feel wonder at the beauty of curved space-time, we are the cosmos experiencing aesthetic appreciation of its own mathematical structure. The realization that we are part of this larger cosmic story, that our consciousness emerges from the same physical processes that govern stars and galaxies and black holes, connects us to something timeless and profound. We are temporary arrangements of matter and energy, brief patterns in the cosmic dance, yet we carry within our minds the capacity to comprehend the eternal mathematical principles that govern all of reality. As your thoughts begin to slow and blur, as consciousness gradually fades into the peaceful darkness of sleep, remember that you are floating through space-time on a small planet, in an ordinary solar system, in an unremarkable galaxy. The same gravitational forces that create extreme time dilation near black holes also keep you gently anchored to Earth's surface, following your natural geodesic through the curved geometry of space-time. Your body is made of elements forged in the nuclear furnaces of ancient stars, matter that has existed for billions of years and will continue to exist long after your brief pattern of consciousness has faded. The atoms in your brain once floated in the cold emptiness of interstellar space, then condensed in stellar cores where they were transformed through nuclear fusion into the heavy elements necessary for life. These atoms carry within their structure the history of cosmic evolution, the story of how a universe that began with only hydrogen and helium gradually developed the complexity necessary for planets and life and consciousness. You are made of star stuff, as Carl Sagan once said, temporary arrangements of cosmic matter that have somehow become capable of contemplating their own existence. The oxygen in your lungs was created in the cores of massive stars that ended their lives in spectacular supernova explosions, scattering their nuclear products across space to be incorporated into new generations of stars and planets. The calcium in your bones, the iron in your blood, the carbon in your DNA, all were forged in stellar furnaces and distributed by stellar deaths across the galaxy. You are part of an unbroken chain of cosmic evolution that stretches back to the Big Bang itself, a direct descendant of the primordial fireball that gave birth to space and time. The atoms in your body are older than the Earth, older than the solar system, nearly as old as the universe itself. You are ancient matter temporally organized into the pattern we call consciousness. This cosmic perspective places your brief life within a context of almost unimaginable grandeur. You are a way for the universe to know itself, a temporary arrangement of matter and energy that has developed the capacity to contemplate the nature of existence. Through your consciousness, the cosmos experiences wonder, curiosity, love, and the deep satisfaction that comes from understanding. The mathematics that describe time dilation near black holes are the same equations that govern your motion through space-time as you rest here on Earth. You are following your world line through the four-dimensional manifold of space-time, tracing a path that began with your birth and will end with your death, yet connects you to the eternal structure of physical reality. In sleep, your consciousness will fade, but the atoms that make up your body will continue their ancient dance, following the laws of physics that have governed matter and energy since the beginning of time. The gravitational field of Earth will continue to curve space-time around you, creating the gentle time dilation that makes your clocks tick, slightly slower than they would in the emptiness of deep space. Your dreams will unfold in the same universe where black holes warp time and space, where galaxies dance their slow gravitational ballet, where the very fabric of reality oscillates with the passage of gravitational waves. The boundary between waking and sleeping mirrors, the boundary between classical and quantum physics, between the deterministic world of general relativity and the probabilistic realm of quantum mechanics. In the quantum world that underlies all classical phenomena, even the vacuum of empty space seethes with virtual particles popping in and out of existence, borrowing energy from the uncertainty principle and paying it back before nature's accounting system can detect the violation. This quantum foam might be the ultimate foundation of space-time itself, the source from which the smooth geometry of Einstein's theory emerges at larger scales. The connection between quantum mechanics and gravity remains one of the deepest unsolved problems in physics. We know that both theories are extraordinarily successful in their own domains, but we don't yet understand how to combine them into a unified description of nature. The solution might require abandoning some of our most basic assumptions about space, time, and matter. String theory represents one attempt to unify quantum mechanics and gravity by proposing that the fundamental constituents of reality are not point particles, but tiny vibrating strings existing in multiple dimensions beyond the three of space and one of time that we experience. In this picture, the different particles and forces would correspond to different vibrational modes of these fundamental strings. Loop quantum gravity takes a different approach, suggesting that space and time themselves might be quantized at the smallest scales, composed of discrete units rather than the smooth continuum that general relativity assumes. In this view, the geometry of space-time would be fundamentally granular, like a cosmic fabric woven from individual threads. These theories remain highly speculative, mathematical frameworks that make predictions we cannot yet test with our current technology. Yet they represent humanity's attempt to push beyond the boundaries of our current understanding, to glimpse the deeper principles that might underlie even Einstein's revolutionary insights about the nature of space-time. Whatever the ultimate theory of quantum gravity reveals, it will likely show us that reality is even stranger and more beautiful than we currently imagine. The universe has already surprised us with the existence of dark matter and dark energy, with the accelerating expansion of space itself, with the deep connections between information and geometry that emerge from black hole physics. Each new discovery reveals layers of complexity and beauty that we never suspected, reminding us that our current understanding, however impressive, is still incomplete. We are like explorers who have mapped the coastlines of a vast continent, but have barely begun to explore its interior depths and hidden treasures. The study of time dilation near black holes represents one thread in this larger tapestry of discovery, one piece of the cosmic puzzle that connects us to the deepest truths about existence. Through careful observation and elegant mathematics, we have learned to see beyond our immediate sensory experience, to understand phenomena that occur in environments so extreme that they challenge the very limits of our imagination. Yet even as we push the boundaries of knowledge ever further, even as we contemplate unified theories and multiple dimensions and the quantum structure of space-time itself, we must never forget the profound simplicity and beauty of the insights we have already achieved. Einstein's revelation that space and time are unified and curved by matter and energy remains one of the most beautiful ideas in all of human thought. The fact that massive objects can literally slow the passage of time, that gravity emerges from geometry, that the universe is a dynamic, evolving structure rather than a static stage for physical events. These insights have fundamentally changed how we understand our place in the cosmic order. They have revealed a universe far more interconnected and elegant than Newton's clockwork cosmos. In this interconnected universe, every particle of matter curves space-time around it. Every photon of light follows geodesics through the curved geometry. Every conscious being experiences time according to their motion through the gravitational landscape. We are all part of a vast, unified system where space and time and matter and energy dance together according to mathematical principles of extraordinary beauty and precision. The black holes scattered throughout our galaxy continue their ancient gravitational influence, creating regions where these principles manifest in their most extreme form. Around stellar black holes, space-time curves so sharply that matter is compressed to infinite density, and time dilation approaches its mathematical limits. Around supermassive black holes, gentler but still profound distortions in the fabric of reality create environments where time flows at dramatically different rates. These objects serve as natural laboratories for studying the most fundamental aspects of physics, cosmic windows into regimes where our normal intuitions about space and time completely break down. They challenge us to expand our understanding, to develop new mathematical tools, to contemplate possibilities that stretch the very limits of human imagination. Yet for all their exotic properties, black holes operate according to the same physical principles that govern our everyday experience. The gravity that creates extreme time dilation near event horizons is the same force that keeps your feet on the ground, that guides the Earth in its orbit around the Sun, that holds galaxies together across cosmic distances. This unity of physical law across all scales represents one of the most profound insights of modern science. From the quantum realm to the cosmic scale, from the briefest moments to the longest epochs, the universe operates according to a small set of fundamental principles that can be expressed in elegant mathematical form. Understanding these principles connects us to something larger than ourselves, something timeless and universal that transcends our brief individual existence. When we contemplate the curvature of space-time, or the relative nature of time, we are touching the same mathematical truths that govern the birth and death of stars, the formation of galaxies, the evolution of the cosmos itself. This knowledge places our human experience within a context of cosmic significance. We are not isolated beings struggling alone against an indifferent universe. We are part of the cosmic story, participants in the universe's ongoing attempt to understand its own nature. Through our consciousness, through our capacity for wonder and understanding, the cosmos experiences itself. As sleep approaches and your conscious thoughts begin to dissolve into the peaceful darkness of dreams, you can rest knowing that you are part of this larger cosmic story. The atoms in your body will continue their ancient dance according to the laws of physics. The gravitational field of Earth will continue to curve space-time around you, creating the gentle time dilation that connects your experience to the extreme environments around distant black holes. Your breathing will slow and deepen, following natural rhythms that have evolved over billions of years of cosmic history. Your heartbeat will maintain its steady pace, a biological clock marking time in the curved space-time of Earth's gravitational field. Your consciousness will fade into dreams that unfold in the same universe where black holes bend light and time, where galaxies spiral through the cosmic dark, where the very fabric of reality pulses with the passage of gravitational waves. In this peaceful transition from waking to sleeping, from consciousness to dreams, you mirror the larger cosmic transitions that have shaped the universe throughout its long history. The formation of the first atoms from primordial plasma, The condensation of the first stars from cosmic gas, the emergence of the first galaxies from tiny density fluctuations in the early universe, all represent phase transitions as profound as the shift from waking consciousness to sleep. Your dreams will carry you through landscapes of imagination that echo the curved space-time around massive objects, where the normal rules of time and causality give way to something more fluid and mysterious. In sleep, past and future blur together just as they do in regions of extreme gravitational time dilation. Memory and anticipation merge into a single stream of consciousness that flows according to its own internal logic. The universe continues its patient evolution around your sleeping form, following the elegant equations that Einstein first glimpsed more than a century ago. Stars burn their nuclear fuel in stellar cores, where matter is transformed according to the principles of quantum mechanics and general relativity. Galaxies rotate slowly through space, held together by the gravitational influence of dark matter that curves space-time but emits no light. Black holes throughout the cosmos continue their gravitational dance, some solitary wanderers moving through the galactic disk, others paired in binary systems that will eventually spiral together and merge in explosions of gravitational waves. Each black hole carries within its event horizon the compressed matter of dead stars, information that may be preserved in forms we do not yet understand. The cosmic microwave background continues to cool as the universe expands, carrying within its temperature fluctuations the imprint of quantum variations from the earliest moments of cosmic history. Dark energy continues to drive the accelerating expansion of space itself, working against gravity to stretch the fabric of space-time on the largest scales. In this vast cosmic context, your sleeping form represents something precious and remarkable. You are matter that has organized itself into patterns capable of consciousness, of understanding, of wonder at the beauty of mathematical truth. You are the universe experiencing itself from a particular perspective, at a particular moment in cosmic time, under the influence of a particular gravitational environment. Your capacity to contemplate these mysteries, to find meaning in the cosmic perspective, to feel connected to something larger than yourself, represents one of the most extraordinary developments in the known universe. In a cosmos that is mostly empty space and simple matter following predictable paths, somehow complexity has emerged that can think and feel and wonder about its own existence. This emergence of consciousness from the interactions of matter and energy might be the universe's greatest achievement, the point at which the cosmos became capable of understanding its own nature. Through your mind and the minds of all conscious beings, the universe observes its own structure, measures its own properties, contemplates its own destiny. In the gentle rhythm of your breathing, in the steady beat of your heart, in the quiet electrical activity of your dreaming brain, the cosmos experiences itself. You are a temporary arrangement of ancient atoms, a brief pattern in the cosmic dance, yet you carry within your consciousness the capacity to appreciate the eternal mathematical harmony that underlies all of reality. As consciousness fades into the peaceful darkness of sleep, as thoughts dissolve into dreams, as the boundary between self and universe grows thin and permeable, you become part of something larger and more beautiful than any individual existence. You join the cosmic symphony where space and time and matter and energy dance together according to principles of extraordinary elegance and precision. In this dance, in this dream, in this quiet moment of rest, you touch something eternal and profound. You are part of a universe that has somehow given rise to beings capable of understanding its own nature, of finding beauty in its mathematical structure, of feeling wonder at its vast scales and profound mysteries. Sleep well, knowing that you are part of this cosmic story, this ongoing adventure of matter and energy exploring the possibilities of existence. The universe dreams through your dreams, experiences wonder through your wonder, finds meaning through your search for understanding. In the cosmic dark, where black holes bend time and space, where galaxies dance their slow gravitational ballet, consciousness rests, dreaming perhaps of infinite possibilities in a universe without end. Tonight, we drift deeper into one of the most profound mysteries our universe has to offer. We've journeyed together through the mathematics of curved space-time, witnessed how gravity itself can bend the flow of time, and contemplated what it means to exist in a cosmos where time is not the steady river we once imagined, but something far more fluid and mysterious. Now, let us explore what happens when we venture into the most extreme gravitational environments known to exist. Places where the very concept of time becomes so distorted that a single hour might encompass decades or centuries in the outside universe, where the boundary between space and time dissolves into something that challenges our deepest understanding of reality itself. As you settle more deeply into rest, allow your mind to drift with me to the edge of infinity, to regions where Einstein's equations reveal truths so strange they seem like dreams, yet are as real and measurable as the gentle pull of Earth's gravity that holds you safely in place. The story we're about to explore begins with a simple question that has puzzled physicists for decades. What would it actually feel like to approach a black hole? Not the violent, dramatic encounter often portrayed in science fiction, but the real, gentle experience described by the mathematics of general relativity. An experience that would be simultaneously ordinary and extraordinary, peaceful and profound. Imagine yourself as an astronaut embarking on the ultimate journey through space-time. Your destination is not just another place in space, but another regime of time itself. You're traveling to orbit a supermassive black hole, one of those gentle giants that reside at the centers of galaxies, where the extreme curvature of space-time creates conditions unlike anything else in the known universe. Your spacecraft approaches this cosmic leviathan slowly, carefully, following a trajectory calculated to bring you into a stable orbit just outside the point of no return. This particular black hole contains the mass of 50 million suns, yet its event horizon stretches across a distance larger than our entire solar system. The scale is so vast that even at the speed of light, it would take hours to cross from one side to the other. As you begin your approach, everything about your immediate environment remains perfectly normal. Your instruments function exactly as they should. Your coffee still steams in its cup. Your heartbeat maintains its familiar rhythm. The artificial gravity generated by your spacecraft's rotation feels identical to what you experienced during the long journey from Earth. Local physics, as Einstein predicted, remains completely unchanged. But something profound is happening that you cannot directly perceive. With each passing hour of your approach, your journey through time begins to diverge more and more dramatically from the experience of observers in the outside universe. It's a divergence so gradual, so gentle, that no instrument aboard your spacecraft can measure it happening to you personally. Back on Earth, astronomers track your progress with telescopes of extraordinary sensitivity. They measure the radio signals from your spacecraft with atomic clocks accurate to billionths of a second. And gradually, they begin to notice something remarkable. Your regular transmissions, sent every hour on the hour according to your onboard chronometer, begin to arrive with increasingly noticeable delays. At first, the effect is subtle. A transmission that should arrive at exactly noon arrives a few seconds late, then a minute, then several minutes. The signals themselves begin to shift toward the red end of the electromagnetic spectrum, stretched by the gravitational field through which they must climb to reach the distant receivers on Earth. This gravitational redshift represents something profound about the nature of light and energy in curved spacetime. Each photon that escapes from your vicinity must expend energy climbing out of the deepening gravitational well. Since photons cannot slow down, they must lose energy by stretching to longer wavelengths, becoming redder and redder as the gravitational field intensifies. Your mission controllers watch this process with a mixture of fascination and concern. The mathematical predictions are unfolding exactly as Einstein's equations suggested they would. Yet witnessing the reality of extreme time dilation creates an almost surreal experience. They are watching time itself become elastic, stretching and flowing at different rates in different regions of space-time. Meanwhile, you experience none of this stretching directly. Your atomic clocks continue to tick with their usual precision. Your biological processes proceed at their natural pace. Your thoughts flow at their normal rate. This is perhaps the most beautiful and mysterious aspect of relativity. Time dilation is not something that happens to you in your own reference frame. It's something that becomes apparent only when different regions of space-time are compared. As you continue your descent into the gravitational well, you begin to notice something extraordinary about the universe around you. Looking back toward Earth, toward the distant stars and galaxies, you observe that they seem to be moving slightly faster than usual. The rotation of our galaxy becomes barely perceptible. The orbital motion of binary star systems appears subtly accelerated. This is your first direct glimpse of the reciprocal nature of gravitational time dilation. Just as distant observers see your time flowing more slowly, you see their time flowing more quickly. Both perspectives are equally valid, equally true within Einstein's framework of relativity. Time has become truly relative, flowing like a cosmic river with different currents depending on your location in the gravitational landscape. The mathematics governing this phenomenon are both elegant and precise. At your current distance of 10 Schwarzschild radii from the black hole's center, time flows at approximately 97% the rate experienced by distant observers. This means that for every hour that passes in your reference frame, about 62 minutes elapse for observers far from the black hole's influence. As you venture closer, the effect becomes increasingly pronounced. At 5 Schwarzschild radii, your time flows at about 90% the rate of distant observers. At 3 radii, it drops to roughly 77%. The progression follows a smooth mathematical curve that approaches infinity as you near the event horizon itself. But something else begins to happen as you approach these closer distances. The view outside your spacecraft starts to change in ways that no amount of description can fully capture. The universe begins to reveal its hidden geometry, showing you perspectives that are literally impossible to achieve from any other vantage point in space-time. Light from distant stars begins to bend and curve around the massive object ahead of you. Stars that should be hidden behind the black hole become visible as their light follows curved geodesics through the warped space-time. This gravitational lensing creates a view of the universe that is both beautiful and deeply unsettling, like looking through a cosmic funhouse mirror that reveals the true structure of reality. The effect is subtle at first, just a slight distortion in the positions of familiar constellations. But as you descend deeper into the gravitational field, the distortions become more pronounced. Multiple images of the same stars begin to appear at different positions in the sky. Some stars appear brighter as their light is focused by the gravitational lens. Others appear dimmed and stretched into arcs and rings. Behind you, in the direction from which you came, the entire visible universe begins to compress into a smaller and smaller region of the sky. Light from all directions gets focused and concentrated by the extreme curvature of space-time, creating what physicists call the optical appearance of approach to a black hole. It's not that space itself is being compressed, but rather that the paths light takes through curved space-time create this visual concentration effect. The black hole itself appears as a perfect sphere of absolute darkness, outlined against the compressed and distorted image of the cosmos beyond. This darkness represents something more profound than mere absence of light. It's a region of space-time from which no information can ever emerge. A boundary beyond which the normal rules of cause and effect break down in ways we are still struggling to understand. As you continue your careful approach, you begin to appreciate the truly immense scale of the object before you. The event horizon stretches across hundreds of millions of kilometers, a boundary so vast that light itself would take hours to cross from one edge to the other. If our entire solar system were placed at the center of this black hole, the event horizon would extend far beyond the orbit of Pluto. Yet despite this enormous scale, the approach to the event horizon is surprisingly gentle. Unlike the violent tidal forces that would tear apart anything approaching a stellar mass black hole, the gravitational gradient around this supermassive object is relatively mild. The difference in gravitational pull between your head and your feet is barely noticeable, allowing you to continue your descent in comfort. This gentleness is a direct consequence of the inverse relationship between black hole mass and the curvature of space-time at the event horizon. Larger black holes create gentler environments near their boundaries, spreading the extreme curvature over such vast distances that local conditions remain surprisingly normal, even very close to the point of no return. As you reach an orbital distance of 2 Schwarzschild radii, the time dilation effects become truly dramatic. Your time now flows at approximately 70% the rate of distant observers. This means that for every hour experienced by mission control on Earth, you experience only about 42 minutes. The effect is now so pronounced that it would be easily measurable with even simple timing experiments. If real-time communication were somehow possible across the vast distances of space, conversations would become increasingly difficult. Your words would sound rushed and high-pitched to listeners on Earth, compressed by the time dilation effect. Their responses would seem slow and deep to you, stretched by the reciprocal time dilation you observe in their reference frame. But in your local environment, everything continues to proceed at its natural pace. Your spacecraft systems operate normally. Your experiments yield exactly the results predicted by local physics. Your biological processes maintain their usual rhythms. The principle of equivalence ensures that local physics remains unchanged, regardless of the external gravitational environment. The view outside continues to evolve in remarkable ways. The ring of compressed starlight behind you grows smaller and more intense. More and more of the universe becomes visible through gravitational lensing, showing you light that has traveled impossible paths through curved space-time. You begin to see regions of the cosmos that would normally be hidden behind the black hole, their light bent around the massive object to reach your eyes. Some of these gravitationally lensed images show you views of cosmic history that are otherwise impossible to observe. Light that left distant galaxies millions of years ago, light that would normally travel in straight lines through flat space-time, now follows curved geodesics that bring it to your unique vantage point. You become a witness to cosmic events from perspectives that exist nowhere else in the universe. At the same time, you begin to observe something profound about the nature of the event horizon itself. From your perspective as a freely falling observer, there appears to be nothing particularly special about this mathematical boundary. It represents simply the distance from the black hole's center, where the escape velocity equals the speed of light, a coordinate transformation rather than a physical barrier. As you approach this boundary, you feel no resistance, no sudden change in your environment, no indication that you are about to cross one of the most significant boundaries in all of physics. The event horizon, from the perspective of someone crossing it, is remarkably unremarkable. Local physics continues to operate exactly as it always has. But observers watching from far away see something entirely different unfolding. As you approach the event horizon, they observe your descent slowing dramatically. The time dilation effect approaches its mathematical limit, causing your clocks to appear to tick more and more slowly from their perspective. Your movements seem to become sluggish, then nearly frozen. From the external viewpoint, you never actually appear to cross the event horizon at all. Instead, your image seems to freeze just outside the boundary, gradually fading and redshifting as the light carrying information about you becomes increasingly stretched and weakened. Eventually, you simply disappear from their view, not because you have been destroyed, but because the photons carrying your image have been redshifted beyond the detection threshold of any possible instrument. This creates what appears to be a fundamental paradox in the description of black hole physics. From the external reference frame, you never cross the event horizon. Your information remains visible, though increasingly faint and redshifted, effectively frozen at the boundary for all eternity according to their clocks. But from your own reference frame, you cross the event horizon in finite proper time and continue falling toward the center. Both descriptions are equally valid within their respective coordinate systems. This is the profound insight that Einstein's theory provides about the nature of reality. There is no single, universal description of events that applies to all observers. What happens and when it happens depend fundamentally on your reference frame, on your location and motion through the curved geometry of space-time. As you cross the event horizon in your own reference frame, you notice something remarkable about the experience. The crossing itself is completely uneventful. There is no flash of light, no sudden discontinuity in your environment, no indication that you have passed through one of the most significant boundaries in theoretical physics. The laws of physics continue to operate exactly as they always have. Your instruments continue to function normally. Your biological processes proceed at their natural rate. The artificial gravity in your spacecraft maintains its familiar strength and direction. From your perspective, you have simply continued along your natural trajectory through curved space-time, following a geodesic path determined by the initial conditions of your approach. The only indication that something fundamental has changed comes from looking outward, toward the universe you have left behind. The compressed ring of starlight that had been growing smaller and more intense suddenly begins to transform. Instead of a ring, you now observe what appears to be a brilliant disk of light, concentrated in the direction from which you approach the black hole. This disk contains the entire observable universe, compressed and blue-shifted by the extreme gravitational field through which you are falling. All the light that can ever reach you from beyond the event horizon is now concentrated into this diminishing region of sky. As you continue falling inward, this disk gradually fades as the light becomes increasingly blue-shifted and concentrated. Eventually, even this last connection to the external universe disappears entirely. You have become completely causally disconnected from the cosmos beyond the event horizon, isolated by the fundamental structure of space-time itself. No information about your fate can ever reach the outside world, just as no information from the outside can ever reach you. The journey inward from the event horizon varies dramatically depending on the mass of the black hole you are exploring. For the supermassive giant you have chosen, the distance from the event horizon to the theoretical center could span tens of millions of kilometers. Your fall toward the central singularity might take many hours or even days of proper time, during which the environment would gradually become more extreme. But even in this relatively gentle environment, the fundamental physics of curved space-time remains inescapable. As you fall deeper toward the center, the tidal forces begin to strengthen. The difference in gravitational acceleration between different parts of your body starts to become noticeable, then significant, then overwhelming. This differential stretching represents the inevitable consequence of the mathematical structure of black hole space-time. The curvature that creates the extreme gravitational field also ensures that objects falling toward the center experience increasingly strong tidal effects. These forces would eventually overcome any material strength, stretching matter vertically and compressing it horizontally in the process physicists call spaghettification. But let us step back from this ultimate fate and consider instead the broader implications of what gravitational time dilation reveals about the fundamental nature of existence. The fact that time itself can flow at dramatically different rates, depending on your location in space-time, challenges our most basic assumptions about the nature of reality. Time is not the universal, absolute framework that Newton envisioned, ticking away the same for everyone, everywhere in the cosmos. Instead, time is local, personal, intimately connected to the gravitational environment in which you find yourself. Each observer carries their own time with them, experiencing their own sequence of moments, their own rate of aging, their own relationship between cause and effect. This relativity of time has philosophical implications that extend far beyond the realm of physics. If simultaneity depends on reference frame, if the sequence of events can appear different to different observers, what does this mean for our concepts of causality and free will? In regions of extreme gravitational time dilation, the very notion of a universal now becomes meaningless. Consider the profound implications for consciousness itself. If you could somehow survive indefinitely in the intense gravitational field near a black hole, you might witness the entire future evolution of the universe compressed into what feels like a brief period of personal time. Stars would be born, live their entire lives, and die in what appears to you as moments. Galaxies would evolve, merge, and transform. The cosmos itself would age around you while you remained relatively unchanged. From this perspective, you would become a witness to cosmic history on the grandest possible scale. You could observe the long-term consequences of physical processes that normally unfold over billions of years. You might see how dark energy affects the ultimate fate of the universe. Watch the last stars burn out. Witness the final transformation of matter and energy in the far future cosmos. Yet this cosmic perspective would come at an enormous cost. You would be forever cut off from the normal flow of human time, unable to participate in the lives and experiences of beings existing in weaker gravitational fields. Your personal timeline would diverge so dramatically from that of the outside universe that meaningful communication or relationship would become impossible. This isolation reveals something profound about the nature of consciousness and its relationship to time. Our human experience is fundamentally based on shared temporal rhythms, on the ability to synchronize our thoughts and actions with others living in similar gravitational environments. Extreme time dilation would make such synchronization impossible, creating a form of cosmic loneliness that is difficult to imagine. Yet there is also something beautiful about the idea of experiencing time at such a different rate. It suggests that consciousness itself might be more flexible and adaptable than we usually imagine. Perhaps beings that evolved in different gravitational environments would experience time in ways we can barely comprehend, living entire lifetimes in what we would consider moments, or stretching brief experiences across what we would consider eons. The study of time dilation near black holes has also revealed deep connections between gravity, quantum mechanics, and information theory that continue to reshape our understanding of physical reality. Stephen Hawking's discovery that black holes emit thermal radiation suggests that these gravitational objects are also thermodynamic systems with well-defined temperatures and entropies. This connection between geometry and thermodynamics has led to revolutionary insights about the nature of information and its relationship to space-time itself. The holographic principle suggests that all the information contained within a volume of space might be encoded on its boundary, implying that our three-dimensional experience of reality might be a kind of projection from more fundamental two-dimensional processes. If this principle is correct, then the solid world we experience, the flow of time we feel, the very substance of our existence might all be emergent properties of information. Theoretic processes occurring on the boundaries of space-time regions. We might be living in a cosmic hologram, where reality as we know it emerges from the complex encoding and processing of information in ways we are only beginning to understand. These ideas push the boundaries of human comprehension, suggesting that the universe might be far stranger than even Einstein's revolutionary insights revealed. Yet they emerge naturally from the careful study of extreme gravitational environments, places where the familiar laws of everyday experience give way to phenomena that challenge our deepest assumptions about the nature of existence. As we drift toward the end of our gentle journey through the mysteries of time and space, let us pause to reflect on what we have discovered together. We began tonight with a simple yet profound truth. Time itself is not the steady, unchanging river we experience in our daily lives, but something far more fluid and mysterious. Near black holes, where gravity reaches its most extreme, time reveals its true nature as something that can stretch, slow, and flow at different rates depending on where you happen to be in the cosmic landscape. We have learned that Einstein's vision of curved space-time is not merely an abstract mathematical concept, but the very foundation of reality itself. Every GPS satellite overhead, every atomic clock in our laboratories, every observation of distant stars confirms that time and space are woven together into a fabric that bends and curves around massive objects. This understanding connects our everyday experience to the most exotic environments in the universe, reminding us that we are all participants in the same cosmic dance of space-time. Perhaps most remarkably, we have seen how consciousness itself emerges as something precious and extraordinary in this relativistic universe. We are brief arrangements of ancient atoms that have somehow become capable of contemplating the nature of time itself, finding beauty in mathematical equations that describe the curvature of space-time around black holes billions of light-years away. In understanding these mysteries, we touch something eternal and profound, a harmony that connects our fleeting human experience to the vast symphony of the cosmos. So as you settle into peaceful rest tonight, remember that you are floating through space-time on a small planet, following your own unique path through the four-dimensional landscape of existence. Time flows gently around you, shaped by Earth's gentle gravitational embrace, connecting you to every star, every galaxy, every black hole in the universe. Sweet dreams, fellow traveler through the cosmic dark.